Hi everybody. I wanted to have a very brief one-sided conversation inspired by Lab 2 and the distance measurements that you made. I want to talk about significant digits in the framework of uncertainty with geospatial data. So we're going to talk about uncertainty and error and data quality a lot in week 6. We're talking about uncertainty, but this is a nice little stepping stone into it and get you thinking about the implications of over-reporting precision, how that's called false precision, and yeah. So anyway, when you hear the word uncertainty with geospatial data, I don't want you to think about mistakes or error necessarily. I want you to think about margins of error. Map locations are very rarely where they are actually mapped. So instead, they are assumed to be found within an acceptable zone around the mapped location. That's what I mean by a margin of error. That for any given point on a map, there is an assumed zone around that point that it's okay for that point to actually be found at in real life. Okay, so what does this have to do with the area calculations that we did with Greenland? Well, it's precision. How detailed is the geospatial data that we're working with? How precisely can we measure distances or areas given the uncertainty that's always inherent in our spatial data? So we need to have some way of quantifying or wrapping our mind around even the iffiness of spatial data and how it is just a representation of reality, but that there is this great amount of uncertainty with the spatial locations represented in it. So first I want to implore you to check out the core concepts page in Canvas. There is a precision topic, and I pulled together this pretty straightforward little demonstration of precision and distance measurements using the Hana Highway in Maui as an example. This is just a little introduction to the idea of precision and accuracy in spatial data, and I hope you'll take a look at it. But anyway, so where are we going from here? We're talking about reporting measurements. And I just want to say that when we report measurements, we are implying the certainty of the data in the precision of the values that we report. There needs to be an agreement between the quality of the data we're working with and the precision of the results that we're reporting. So in this example, if you report a value of 14.5 meters, you're implying a spatial accuracy, a horizontal accuracy of 1/10 of a meter. A round integer reporting of a distance like 14 meters implies an accuracy to the nearest 1 meter, horizontal accuracy. This is just a rule of thumb. A lot of people would argue that with raster resolution, if you have a 10-meter cell, it's legitimate to report the distances to the nearest meter. But this does get really complicated, and we're going to go into it more. I'll provide you with some resources when we get into week 6. So you should be thinking about rounding your values to bring them into alignment with the certainty of your data. So one question is, how do we know what the quality of the data is? Where do we find these horizontal and vertical accuracies that we can use to guide us when we're making these rounding decisions? One place to go, the FGDC is the Federal Geographic Data Committee, and they are sort of the police, the geospatial data police for how we're going to report our data quality. This is a good, if you just Google the fgdc.gov, there's a really great website here that talks about all the spatial data. I don't know what you want to call it, the structure that we report the quality of our data in. The data quality information is a nice kind of write-up. It's the syntax that you'd expect to see in these data quality reports. The one thing you'd want to be looking for is the horizontal accuracy. This is just going to be some numeric value. It's usually an RMSE, a root mean square error, but it kind of lets you know to what degree you can trust this data. This is going to be usually found with raster data, not as often found with vector data, but you should know about it anyway. Okay, so when we're dealing with paper maps, there's a general rule of thumb that says that any given position on a map needs to be accurate or will be accurate within about 0.5 millimeter. So that's the general rule of thumb, but this is true for paper maps. But it's a pretty good rule of thumb because it applies out. If I think about all the different ways I know of quantifying spatial error dependent on scale, this works out to be fairly true. So generally speaking, a 0.5 millimeter on the map, if you multiply it out, that just means that with these different map scales, we would expect any given location to be found within, like this is a world map scale, within about 50 kilometers of its map distance on paper. We don't know which directions, so when we start talking about areas, this becomes the radius of a circle, and our area is obviously much bigger. And the other thing to note here, this is a standard set by the USGS. It's a national map accuracy standard, and they only require that 90% of all points on a map fall within this margin of error. So we're just talking about 90% of the data, so this also becomes a bigger number when we start dealing with that, a more erratic 10%. So anyway, what does that mean for us when we're dealing with geospatial data that's downloaded from web sources? You need to know that often data downloaded from commercial or government sources will come with a metadata file that's going to give you this kind of horizontal accuracy information. It will come structured in the syntax of that web page I just showed you. This guy. It will look a lot like this, but this will all be populated with information that's relevant to your data set. Another place to look is the metadata of the file itself, and you can do that in ARC Catalog. This is a great example because this is what you'll usually find. And so in ARC Map, remember there's that little ARC Catalog shortcut that we can open over here, but that's a shortcut to a kind of a limited version. Oh, I'm going to have problems here. Limited version of ARC Catalog. You want to go into the Startup menu, into your ArcGIS folder, and open the full ARC Catalog. That way you can go to any data set that you want, and if you go to the Description tab, this is the metadata report for this data set. This is the country shape file that you pulled the Greenland data from, and you can see there's just nothing here. This is calculated from the data itself. We are given the data credits, and if you follow this link back to the DIVA GIS website, you won't find any really obvious metadata files. So you are sort of on your own in this case, for better or for worse. But it turns out that visual inspection is a pretty decent way to evaluate vector data at the very least. So if we go into ArcMap and take a look at this data set, zoom to Greenland here, we can look around for some, we can zoom in and just look for how closely this data matches. Usually with vector data, what it means is that there is a certain size of feature that just won't be visible anymore. And you can see that's true. There are a lot of little islands out here that have just been left unmapped, and that has to do with the generalization that's required of a map of global scale. There's a definite offset here, which is a kind of a systematic bias, but it doesn't look like there's a serious loss of error. It's just loss of area. It's just more of a shift. But there are some little islands here that have been left off. If we try and calculate the measure the distances of these, they're pretty small. So 2 kilometers by 2 kilometers maybe is a pretty standard feature size to be dropped at the global scale. There's also going to be some generalizations, and you can see that here. Even with the offset, there's a real generalization of the complexity of the outlines. Just zooming around a little bit, this is going over to the east side. You can see there are some places that are probably representing temporal uncertainty or temporal error, where there maybe was a lobe of a glacier here that it's calved off. This glacier here may have receded back. So we still have offset but not loss of area, except for there are some good examples here where the area of Greenland is being over-reported, and it's very possible that that this glacier is sitting on open water and there isn't land underneath here anyway. So that's another level of uncertainty, is we really don't know where the land is. My guess is this is open water underneath here, but we don't have any way of knowing. The other place that was kind of interesting was all up in the north here, and again, I don't know whether or not we should attribute this to temporal errors where we just have recession here, or if it's data offset, a shift. In some places it looks like it's mapped really closely. In other places we have some pretty serious over-reporting of the area of Greenland. So we need to take these things into consideration. We could add other base maps and check them against some of these other sources that we have. We could pull in the USGS stuff and just see if it's any higher quality. The other thing I did is brought this into Google Earth. Hang on one second. All right, so I created a KML file of Greenland so that we could inspect it over time using some of the historical image features that they have. You can see already that some of that same error is present up in the northern part of Greenland. So again, it's hard to know what to attribute that to. But if we use the time thing here and go all the way back to the beginning, it's hard to know how far back the data really goes. But there are some pretty cool data sets that come in here. Don't necessarily tell us a lot, but just know that this is another way that you can kind of get to know your data a little bit better and inspect it. This is kind of an interesting one, maybe. Yeah, it's hard to know what's going on here too, if that's just, yeah, I'm not really sure, but it does look like there are a couple different resolutions happening here. What can we see in different data sets? It looks like they brought in another data set here too. Well, anyway, obviously they're trying to get some higher resolution data to track, whatever their project is, but glacial loss, landscape change doesn't really give us a big enough picture to be able to evaluate the resolution of our vector data. But anyway, this is a handy tool, I think, if you want to visually inspect the accuracy of your data, going into Google Earth and using the time scale, the time slider. That's pretty cool. Okay, so given all that, what are we going to do? What's the moral of the story? The moral of the story is you should be able to defend pretty clearly the agreement between the precision of the values that you're reporting. Like I say in this precision thing, if you have a data set where you have a reported horizontal accuracy of plus or minus a meter, and then you go and measure a distance of a road covering, some distance, some spatial extent, you wouldn't want to report the distance of that road to the nearest millimeter. You wouldn't want to have 6 decimal places or anything like that. It's just you need to have agreement between what you're reporting and your data quality. I'm going to leave it at that. I've babbled enough. No, I'm going to leave it with this. And if you have questions about this, please let me know. Thank you.